Ever wondered what pointers are in C++ and why they are important? Well, you're in the right place. Pointers are a fundamental concept in C++, a crucial tool in a programmer's toolbox. They are variables that store the memory address of another variable. So how do we declare and initialize a pointer? It's quite simple. We use the asterisk symbol, asterisk, to declare a pointer. Let's say we have an integer variable named number, and it's assigned the value 42. We can create a pointer to this variable by declaring a pointer variable, ptr, and assigning it the address of number. This is done using the ampersand symbol, and, which retrieves the address of a variable. Now you may wonder, how can I access the value at the memory address stored in the pointer? And that's where dereferencing comes into play. We use the asterisk operator, asterisk again, but this time it has a different role. When used with a pointer, it retrieves the value stored at the memory address that the pointer is pointing to. But what if a pointer doesn't point to any valid memory address? In that case, we use null pointers. A pointer can be assigned a special value, null ptr, to indicate this. Initializing a pointer to null ptr is a good practice, as it prevents accidental misuse of uninitialized pointers. In some cases, we might need to navigate through memory. Pointers offer a way to do this using pointer arithmetic. We can increment or decrement a pointer, and even perform arithmetic operations on it. Now that we've covered the basics of pointers, let's delve into how we can use them. In the following scenes, we'll explore more about dereferencing, null pointers, pointer arithmetic, and finally, pointer-based strings. So stick around as we unlock more secrets of pointers in C++. Let's dive into the world of dereferencing and null pointers. Dereferencing is a process that takes us from the address to the value. It's a bit like having a treasure map. The pointer is the map, and dereferencing is the act of following the map to find the treasure. In C++, we use the asterisk operator to perform dereferencing. If we have a pointer, say, ptr, pointing to an integer variable, number, we can access the value of number using the expression asterisk pptr. This is like saying, give me the value at the address stored in ptr. Now imagine you have a map, but there's no treasure marked. That's akin to a null pointer in C++. A null pointer doesn't point to any valid memory address. It's a special kind of pointer that signifies the absence of a value. You declare a null pointer by assigning it the special value nullpr. This is a safety measure. It's always a good practice to initialize pointers to nullptr if you don't have a valid address to assign. This way you avoid what we call a wild pointer, a pointer that points to some random memory location which can lead to unexpected behavior, or worse, program crashes. So in essence, dereferencing is the act of accessing the value stored at a memory address, and a null pointer is a pointer that doesn't point to any valid memory address. It's important to note that dereferencing a null pointer leads to undefined behavior, often resulting in a program crash. That's why it's crucial to ensure that a pointer is not null before attempting to dereference it. In the world of C++, pointers play a vital role, and understanding how to use them, dereference them, and handle null pointers is an essential skill. It's like mastering the treasure maps of programming, where the treasure is your data, and the map is a pointer. Understanding dereferencing and null pointers is crucial when working with pointers in C++. Did you know you can do arithmetic with pointers? Yes, indeed. In the world of C++, pointers are not just for storing memory addresses. They also have the ability to perform arithmetic operations. This is a facet of programming known as pointer arithmetic, and it's a powerful tool for navigating and manipulating data in memory. Pointer arithmetic allows us to increment or decrement pointers and perform other arithmetic operations to navigate through memory. It's a bit like having a map and compass in the wilderness of our computer's memory. Let's visualize this with an example. Imagine we have an array of integers. We can create a pointer that points to the first element of this array. Now, if we increment this pointer, it doesn't just increase by 1. Instead, it jumps to the memory address of the next element in our array. This is because in C++, the size of an integer is typically 4 bytes. So when we increment the pointer, it actually moves forward by 4 bytes in memory. This ability to traverse memory can be incredibly useful. For instance, we can access the third element in our array using pointer arithmetic. To do this, we add 2 to our pointer, effectively jumping over 2 integers in memory, and then dereference the pointer to access the value stored there. But what happens if we try to increment a null pointer? Well, C++ defines this as undefined behavior. This means that the result is unpredictable and can lead to unexpected results or even crashes. So it's crucial to always ensure your pointers are pointing to valid memory addresses before performing arithmetic operations. Just as we can increment pointers, we can also decrement them, making them point to previous elements in memory. And if we have two pointers pointing to elements in the same array, we can subtract one from the other to find out how many elements apart they are. Pointer arithmetic can seem a bit abstract at first, but with practice, it becomes a powerful tool in your programming toolkit. It allows us to manipulate and navigate data in memory with precision and flexibility. And that's how pointer arithmetic works. It's a powerful tool for manipulating data in memory. Now, let's turn our attention to pointer-based strings, also known as C-style strings. In C++, strings are represented as arrays of characters, where each character occupies 1 byte of memory. These arrays are terminated with a special null character, represented by E0. This null character signals the end of the string, allowing for functions to know when the string terminates. To declare and initialize a C-style string, we use a char array. We can also use a char pointer that points to the first character of the string. For instance, consider the following declaration: const char asterisk str equals sign hello world. Here, str is a pointer to a character constant. It points to the first character of the string hello world, which is A. Accessing individual characters within these strings can be achieved in two ways. First, we can use array notation, treating the string as an array of characters. For example, char first char equals sign str will assign the first character of the string to the variable first char. Alternatively, we can use pointer arithmetic to navigate through the string. For example, char second char equals sign str plus 1 will assign the second character of the string to the variable second char. For manipulating these C-style strings, we have a set of functions provided by the header. Functions like strlen can be used to get the length of the string, strap to copy strings, strcat to concatenate strings, and strcamp to compare strings. But what if we don't know the size of the string in advance? This is where pointers truly shine. We can dynamically allocate memory for the string using the new operator. For example, char asterisk dynamic star equals sign new char allows us to create a string that can hold up to 20 characters. After we're done, we must remember to deallocate the memory using the delete operator to prevent memory leaks. You've just learned the basics of pointer-based strings. Let's dig deeper into this topic. Scene script. Let's explore how to manipulate pointer-based strings. We've understood how to declare and initialize pointer-based strings. Now, let's delve into their manipulation. C++ provides a variety of functions for manipulating C-style strings, housed within the CSstring header. For instance, the strlen function helps determine the length of a string. It starts counting characters from the beginning of the string and stops when it encounters the null character. So if we want to find the length of our string, hello world, we just use size underscore t length equals sign strlen, str. Now, if we want to copy our string into another character array, we use the strp function. Here's how. Char destination, strcp destination str. Now, the destination array holds a copy of our string. To concatenate strings, or in simple words to add one string at the end of another, we use the strcat function. For instance, if we want to add C++ at the end of our string in the destination array, we just say strcat destination C++. Comparing strings is also a common operation. We do this using the strcamp function. It compares two strings and returns an integer indicating whether the first is less than, equal to, or greater than the second. Now, there's an interesting aspect of C-style strings. We often don't know their size in advance. This is where dynamic memory allocation comes into play. We can allocate memory for a string at runtime using the new operator. For example, char asterisk dynamic star equals sign new char. Don't forget to free the allocated memory using the delete operator once you're done with it. While C-style strings have their uses, it's important to remember that modern C++ provides the std string class. It's a convenient and safer alternative. It automatically manages memory and offers a wide range of string manipulation functions. But understanding C-style strings is still valuable, especially when dealing with legacy code. And that wraps up our discussion on pointers and pointer-based strings in C++. Remember, practice makes perfect, so keep coding.